Hi guys, today we're going to talk on color, the second last part of the whole series. You must understand color. Why is there color in the world? All right, you must understand this thing called the electromagnetic spectrum. This spectrum, this whole range of wavelengths all here are found in the world everywhere. Of course, gamma rays, for Incredible Hulk, it means the smaller the wavelength, it's very small, this wavelength, right? The wavelength, the smaller wavelength, the bigger with the wavelength, kind of thing. Okay, small wavelengths are more powerful, more energy, right? Because you can see energy is equals to H frequency, or sometimes H, this also frequency, or H is the Planck constant, C is the velocity of light in a vacuum, or over lambda. Now this is the wavelength, okay? Wavelength. So we normally talk about wavelength on the color, right? So you can see the range of the X-rays here, also very powerful. UV, also very powerful, they cause skin cancer. Infrared, also powerful. Radar here, FM radio here, TV here, shortwave radio, AM here. Now, of course, this is a very small portion of the electromagnetic spectrum. Is what we call visible light. It's colorless. It's colorless. It's white light, no color. But it's made up of all these colors, and it is analog, not digitized. So in Form 5, you learn is red, okay, orange, yellow, green, blue, violet, indigo, right? So these are all the main colors of the visible light. It's all this wavelength here, right? Between this small part of 400. Remember, it's good to remember the wavelength, the meters are 400 is in meters here, right? Oh, sorry, nanometers here. 400 nanometers, and which is the shorter the wavelength, the more energy, which is your violet or indigo, okay? Indigo or violet, okay? And between here, which is red, okay? This red here, which is about 800, let's say, or actually 750, around 750 nanometers. Okay. So in the middle, you must always remember is yellow or green. They will ask you one, okay, very important. You can say either yellow or green, okay, this green, this yellow, okay. So it's this spectra, this small part here of the electromagnetic spectrum of the whole universe, right? Is where the color comes from. Okay, now how do you explain color in the world? Right. Now remember light, when light comes, see, there are two things here. Now this now this is the object. Why is it red here? Okay, so when white light comes in, let's say it's solid. When white light comes here, white light, okay, visible light, which means it contains all the different colors of the rainbow, comes here, it will absorb all the colors except red. So here, okay, all colors absorb, and red is reflected. Okay, so, or if you want to, this is solid, if it's a solution which you are more keen on, if it's a solution here, okay, let me put a blue solution, okay, right, blue solution. It's copper 2 plus, okay, copper 2 plus solution, right? So what happens is that white light comes through, come here, white light, and all the colors other than blue is absorbed. All colors except blue is absorbed. Now here, absorbed. What is unabsorbed? This is called transmitted. That's what transmitted. Transmitted is observed. This is blue. See now, So that's how it is, okay? The things are always absorbed. Things are always, if it's solid, it's reflected. If it's solution, is transmitted. Okay? So we are talking about this one here, transmission of light. Okay? So here, solutions undergo absorbance of the wavelength and transmit. All those that are not absorbed. Solids, they absorb, and whatever that's not absorbed is reflected. Okay? Now this is a good thing here. Sorry. Here it gives you what you call complementary colors. Complementary colors. I want to say this word because this one comes out in exam marking scheme. Let me show you. Okay, now I got a marking scheme cut out here so that you can see LE and not LI. Okay, color observed is the complement of the color absorbed. Observed, absorbed. So there are two basic colors. Okay, so let me just maybe ask you a question now. Okay, let's say I got here, all right, here, right? Let's say you are wearing a green shirt, okay, green shirt, green. Okay, so let me go back to the part there. It doesn't seem to move. I don't know why something gets stuck. Okay, yeah. Okay, you are wearing a green shirt. Okay, I'm playing green. So in a white light, it's a green shirt. All right. So now in the open light here, when light comes in here, all right, light comes here, okay, they absorb all the light except green. So green is reflected. It's not. Green is reflected. Green reflected. Now you look at here, green. Observe green. Okay, green shadow green. Okay, I think don't use green. Use blue, but okay, green can. Green. They say green here. The complementary color is red. Okay, red. I put red here. Okay, that means that basically this shirt absorbs red wavelength. Okay, green wavelength unabsorbed. Unabsorbed. So let's say you take this shirt and go into a dark room. Okay, dark like go a movie theater. Okay, go into a movie theater here. Dark. So you put a green shirt inside here. Okay, and you shine a red light into it. What do you see? What kind of shirt you see? Black, isn't it? Because you have absorbed all the red color. So you won't see anything. You see black. You can't see the shirt. See? Because it will absorb all the red colors. That's why it's called complementary color. Okay? So these two are complementary. Absorb this, you see this. Absorb this, you see this. When these two mix together, it comes black. Okay? So remember everything in your in your transition metal we talk about well, remember in your transition metals we talk about compounds and ions have color. Okay? We don't talk about elements. Let's say, for example, look at this question here. Okay, let me look at question page 82. All right, it's good to ask this kind of question. You see? Explain detail why transition element compounds. Why don't they say transition element? Okay, why do they put this on here? If it's transition elements are not colored, because transition elements are metal, and metal, what color is metal? Metal is shiny because of the electrons there. So there's no color for elements. It's only color for compounds. And compounds are formed when the transition metals, like for example, copper, becomes copper 2+. So it's only ions that are colored, not the elements. The metal has no color. The metal is just shiny gray. Okay, so remember, it's very important to know the concepts, all right? Okay, this is the compounds. The compounds are often called compounds, see, which means ions, 1 plus 2 plus 3, whatever. Okay, so let's go back to the color, page 54. Okay, now, so we talk about the idea of color. So what happens when your ions, for example, titanium or copper, I see here's moving. Okay, when copper 2 plus, when white light comes in, well, this fellow here, and all these are colored. If they're colored, that means they must have absorbed some part of the frequency of your white light and reflected the color, which is the blue color. So if they reflect blue color, that means they must be absorbing orange color, this wavelength. So what happens in this ion here when it absorbs this wavelength? Something happens in. Well, yes, see, remember, there are electrons inside here, and the electrons can move to different shells. Remember not, okay? S, P, D, F shells can move up here at the empty shells. So electrons are promoted. Remember, when energy light is absorbed, see here, right? Electrons are promoted from a lower energy to a higher energy level. Now this is 1 mark. See the markings here? Right? It's very good to see how markings can be seen. Light is absorbed. 1 mark. Best to say, light in the visible region is absorbed. What happened? Electrons are promoted from a lower to higher. 1 mark. See, 2 marks. Color absorbed is complement to the color absorbed. That means this light which is absorbed, right? Absorbed, and will be complement to the color, the color of the light that is not absorbed, which is the observed color, right? And we come to this afterwards. This is the energy difference between the two levels of energy. Okay. Now, so idea that electrons are promoted when you absorb the visible region of light. Now, why are some substances colorless? For example, sodium chloride. You will always compare with group 1 and group 2. The famous one, of course, is calcium, right? Remember, plus calcium is a metal, so if we talk about calcium metal, it is shiny, is it not? Right? It is solid, shiny metal. But calcium 2 plus ions are colorless. Why silicon is colorless, and why, of course, sodium chloride is colorless? Right? That means nothing in this visible region is absorbed, all pass through. So why? Now let's look at this first, okay? Now, sodium, remember? Now this is, sodium is what? Sodium is Na, I think I got it down here. I wrote this now. Not here. I think I wrote up here. Not here, never mind. Here. See, sodium metal is 11 here. Sodium metal, now no charge here, is 0 charge here. 1s2, 2s2, 2p6, 3s1, okay? So when sodium loses 1 electron, when it loses the 3s electron, okay? So 3s here is empty. It's the next level, okay? Right, next level here. For example, you can see here, right, now here, 2s. Let's say I put 1s down here, okay? Just to make it 1s. So 1s2, 1, 2. 2s2, 1, 2. Okay, now this is your sodium, Na plus. 2p, 6 of them. 2px, 2py, and 2pz. And this is empty. And this is the next. This is the next level. This is the lowest energy level you can find, those heat, H heat, okay? It's equals to Hc lambda. So they found that when light comes in, or when any electromagnetic spectrum came in, this electron, any one of these 6 electrons here, right? Any one of them here, this one, or this one, or this one, or this one. Remember, they are all of the same energy level. They can be promoted from here to here. Okay, so if one of them come out here, okay, so here, this is okay, here, this one come out. Okay, so it will go up to here. Now this energy is given by this one here. Remember, H is a Planck constant, is a constant, C is a constant. So this is the frequency, this is the wavelength or the frequency for it to jump from here. We found that this wavelength here is in the UV region. It absorbs UV light and boom, go up to here, 3S1. You go to 3P1, even higher energy now, right? The UV region. So that's why none of the visible region is absorbed, so it's colorless. Because 3P, 2P to 3S, right? 2P to 3S, the delta E is equal to this, and the lambda here is in the region of the UV. Okay. Now chloride, same, Cl minus, right? Cl minus, remember Cl? Okay, chlorine. Chlorine is of course 17. 1s2, 2s2, 2p6, 3s2, 3p6. It's not right. Well, let me see. 10, 18, 3, okay, 3p5 lah. Sorry about that. 3p5, 17 okay. But when it plus an electron, right, it goes to what? Cl minus, right? 1s2, 2s2, 2p6, 3s2, 3p6, okay? 18, so it will be 3p here, right? Here, this 3s, 1, 2, and here be 1, 2, 3, 4, okay? So they found that if Cl minus were to absorb a wavelength, the electron will be promoted from here to here, 3p to 4s. Right, there's the next level. Of course, there's 3, there's a 4p, and there's a 4d, but they are higher energy levels. So of course, the nearest one is here, 4s. They found that this level here, this energy level, okay, that change of E equals to HCO lambda. Even this is in the UV region. That means it will absorb energy from here, it will go to here. But this here to here, the wavelength is in the UV region. That means none of the visible region is observed. That's why Na plus and Cl minus are colors, okay? Because none of the visible part, none of these colors is absorbed because the energy is too high, right? Now, titanium. It's very important to know what they write here. Titanium is gas. Gas means no ligands, okay? They are gases, Di3 plus. Gas means no ligands, or they call it an isolated ion. Isolated. Ti3 plus ion. Isolated means no ligands. As compared to here, got ligands. That means this is in water already. Okay. So now titanium. Titanium, as you know, right? Let's quickly go to that. Right. Ti3 plus is Ar. Okay, and 3D1. You look at yourself, okay? 3D1. The 4s2, right? Actually, it's 4s2, 3d2. So 4s2 come out, and one of the 3d come out. So it's 3d1. So what you got here is 1, 2, 3, okay? Right, and then 1 here. Okay. Remember, D has got 5 degenerate orbitals. What do you mean by degenerate? Means same energy. Different states, but same energy. So they found that, well, in this case here, right, titanium, if it were to absorb any energy, right, the next level it can go is from 3D1 to 4S1 to here. Okay, I'm going to put a different color here to here. Right? For gas, that means no ligands. From here to here, the delta E, they found that HCO lambda, the lambda here is still in the UV region. Okay, so for gaseous state, for gaseous state, you cannot explain. There's no color for gaseous state. So you cannot use the 3D to 4S. Okay, but they found that in aqueous, any complex ions, Now here is what they did an experiment on. You see? All right. Now this is the absorbance. Absorbance. What they did was, of course, they used what I call a colorimeter. Right? I think you've done this before, colorimeter in your rate of reaction. Okay, I'll show you what I mean. What it is here. You can see actually here. Okay, I hope I got it right. That's all. No, it's on complex here on top. Sorry, I didn't learn to use it on, but since I mentioned it, I might as well show you what are here. Now, okay, now the two here, right? We'll do this later. So, come on. Okay, yeah. Now this is a colorimeter. All right, let me rub off a bit things here first. Okay. Now, see, I will put the titanium chloride, okay? Titanium chloride here in the cell here. Ti, okay, Cl3 aqueous. See, Ti Cl3 aqueous will actually give me Ti 3 plus aqueous plus 3 Cl minus aqueous. This one I know that no color. No color. Why? Because we are explaining just now, it will only absorb 2p, sorry, 3p to 4s in the UV region. Okay, so it's colorless. So this, they found that this titanium 3 plus, right, is violet in color. Your gemstones, okay? So they put this titanium 3 plus aqueous, which is Ti, water is H2O6, why not? Okay, hexa aqua 3 plus here into this thing here. This is called your optical cell. Okay, and then they put a bulb here, which is white light. White light. Okay, I put a filter here, right? Okay, then the filter will pass different lights here. Okay, you can change it from red, go to orange, go to yellow, go to blue, go to violet, go into gold. Here, the filter, they can adjust the frequency, nanometers. Okay. So here you can see whether as a pass through here, whether it will absorb or not. Okay. If it absorb, that means go down. Okay. Right. So here. So it will absorb here. Now, so what they see is that is, and then the meter will read up there. Okay. So you can see here. Okay. So this is absorption. Right. So they found that, whoa, down here, blue and violet is not absorbed, no, but they absorb the green. That means this part is being absorbed by the titanium 3 plus equals. That means this part here, or yellow green, okay, or green, but green, okay, is absorbed by this ion. There must be a transfer of electron from a lower energy to a high energy. Right? Okay, so how can that happen? So as I said, it cannot happen from a 3D to a 4S, because from here to here, the wavelength is still in the UV region. Okay, found out. So what happened was they say, well, okay, there's something called crystal field splitting theory. Now, this is what happens. Now watch out. Now this is how they explain it. Now this is the gaseous ion. Okay, titanium 3 plus aqueous. Sorry, not aqueous ion. That means it's an isolated ion. And now there are 5 orbitals. 1, 2, 3, 4, 5. You must know how to draw all this. Okay, there's dz square, dx square minus y square, dxy, dyz, and dxz. Now, you can see from here. Okay, or this is a better diagram now. Okay, now because it's an octahedral axis, okay, they're all right angles here, z, x comma here, and y here. Okay, now this dz square has the orbital going up like that and down like that. Okay, Actually, there's another one, but this like a ring here, this like a certain ring. Okay, don't care. Okay, is this two loops that's along the x-axis, and then dx square must no, right? Why is jam? So here, dx square minus y square. That means that this is coming out from here. That means the loop is here, then go to the back. Okay, so the x is coming out here, and your and this is your z, this is your x, this is your y, y. So the loops are right. The loops are pointing along the axis, right? The dz is here. So these are all the axes of the octahedral complex. Of course, the dz dz. Remember the z here and your x here. You can call it dxz also. It doesn't matter. Okay, it's sort of in between here, in between the two axes here. 4 of them also. Okay, and of course here, let's get started again. dyz. That means it is between. I don't know why it's stuck. Am I? Okay, it's playing up to me. Okay, this is your z here. So this is your y here. So it's between here and here. Okay, here there are 4 of them. Again, the x, y wrong here and here. Remember when there's no difference in when there's no ligands, they all 5 of them are degenerate. Degenerate. Okay, which means what? They all same energy. That means the electron can fit anywhere. Remember, there's one that you have only for your titanium 3+ one, you have only D3D1 as well. Right? There's only one electron. The electron can go to any one of them. So, keep on going because same energy level one. Okay, if I give you 5 rooms there, charge the same, right? You can go any room you like. You can move from room to room. Same, because same energy level. But the point is, once when you have here, if you see here, a complex ion here, see, right? This is the aqueous complex ion, see now, which is Ti H2O 6 bracket 2 3+, sorry, okay, 6 over here. Now these 6 water ligands, now remember the ligands are this here, okay? The lone pair here will form the positive. No, this delta negative, delta positive. Right. The ligands will form the bond with who? With where? With the d orbitals. And of course, since it's going to enter into the octahedral, right? That means it's going to come face here, and here. Water. And here. Water. And then here, so you want to talk about the thing here. Come here and here. O and water here. Okay? And so of here, oxygen going to here to form the daily bond here. And here. Right? That means all of the d orbitals lying along the x, y, z orbitals when the electron is here, the electron can be here, here. Okay? When the electrons come here, this electron here will feel repulsion with the lone pair. Okay? Because there's repulsion here, there's repulsion. Therefore, the dz square and the dx square will have higher energy than these 3 fellows here. This is called splitting. So the d orbitals will split into 2 parts. See now, right? 2 parts. The dz square and the dx square minus y square will have high energy because why? The lone pair of electron, the lone electron pair of the ligand. In this case, of course, oxygen, right? Right? Facing what? Facing the dz square orbitals and the dx square minus y square will cause these two to have high energy. Go up here. Only a very small difference only. Okay, very small difference. The E here. Okay, very small difference. Okay, H, which means this difference here. So remember, now of course, now there's no electrons here. Okay, remember I told you already there are only 1 electron, 3D1, okay, titanium 3+. So what happens is that this fellow here, right? Now this is in the dark. ground state, stable state in the dark. No light yet, right? Now, when light comes in, light shines in this way here, light comes in here. This electron will resonate or will accept or will absorb one of the frequency in the visible region to be promoted from here, see now, from here to here, go up here. And that frequency is fixed, you know, because see, energy level is fixed. These two are constant. That means it's fixed. They found that from here. So which light will the electron absorb to be promoted up there? Huh? Which light? You can see from here, from the experiment, is which light? Huh? Which is that? Yeah, green light there. See? All these lights are blue and violet, and the red is not absorbed. That means these two will pass through there. So it will pass through the titanium, A equals here, 3 plus, it will pass through here. And violet and blue and red will pass through. That means these two combinations will give you a violet color, a purple color. What is absorbed here? Absorb is a green color. And when absorb, it will transmit the electron from D to D. So this is called a D to D. See? This is called a D to D electron transmission. Or D to D electron promotion. That means it's a very small energy difference only. And this difference here, the frequency is in the visible region. One of the light will be absorbed, but the rest of them will just flow through. That's why. Okay. So that's why for color, there must be an M. That means the d orbitals must be partially filled. That's why for it to be a TM, at least one of the ions must have a partially filled d orbital. Otherwise cannot be. That means they will have no color. Okay. That's why zinc 2 plus no color because the 3D are all completely filled. Scandium 3D 0, right? No electron transfer. These two here, no D to D electron transfer. That's why it cannot. It will absorb energy, yes, but always from the UV region, never from the visible region, because that's too small the energy level. Okay. Now that one, of course, is the copper. Okay, copper. Now here I explain here. You can see last time this is very popular. See why the DD split. The lone pair electrons in the ligands pointing. This is very important. What they want pointing towards the electrons of the d orbitals in the central ion will have higher energy due to repulsion. Electrons in the dz square and the dx square minus y have their orbitals along the axis of the octahedral, and the lone pair electrons pointing towards them. Therefore, the dz square and dx square minus y have a higher energy level. Okay, you can see the wordings are very important. I took this from marking scheme now. Okay, now the other one, of course, is one here. You can see copper 2 plus. One here they ask copper 1 plus. Okay, for copper 2 plus. Okay, so copper 2 plus is 3 if AR 3D9 because copper is AR, right? 3D10 and 4S1 because why? 3D10 extra stability. So when those two electrons lose out, and of course lose one from here, so 3D9. Now, so this is the degenerate state, 3D orbitals. Because why? This is the isolated ion. Copper 2 plus gas. Okay, no ligands. Okay, so it's all safe. So one here only. Okay, 2, 4, 6, 8, 9 here. So when here you have got copper, see here. When you have copper hexa aqua 6. Okay, 2 plus here. The water will come along the octahedral complex and point towards the dz square and x minus y and cause this 2 to be split 2 levels. This now called non-degenerate. Okay, these 3 are degenerate, these 2 are not. So now this energy is a difference here. Okay, so this delta E you can see is equals to Hc over lambda. That means when you put copper 2 plus solution, this blue, okay, copper 2 plus. If you put white light here, and you see blue color, that means what is absorbed? All the colors except blue. Mainly, what's the complementary color of blue? It's very similar to see actually orange. Okay, it's very, very important. These two, you must remember later you will see it's quite important one. here, the complementary colors. Okay, blue is, for blue is what? Orange now. Blue, orange, 600 nanometers. That means they will absorb a lot of this one here. Won't go down, don't know why. Okay, never mind. Here we are. So here, you absorb here, and this is the orange color. Orange color. Absorb. So blue color is not absorbed. Absorb. But now is it observe? Very important, they will ask you one. Observe. Okay. So that's why there's color. Okay. Right. And sometimes if see different ligands will split this into different energy levels. Right? That's why sometimes for Cn minus one, it's very strong. So it's split into a very high level. That's why copper, Cn4, 2 negative, is colorless. Why? Because the D and D is so big. The frequency here is in the UV region. Sorry, HC is in the UV region because this is so big. So try to say here we have, see, Cn is colorless, isn't it? So we have different splitting. Ligands have the ability to split the d orbitals differently. This is the biggest. Okay. Now water is here and ammonia is here. Okay, this one here, the water will split in a smaller difference between the D and D. Ammonia will split in a bigger difference. That's why this is pale blue. And this is deep blue. Okay, you can see that pale blue and deep blue, there's a difference here. Right, pale blue and deep blue. All right. You see here? Okay. All right. Pale blue, you see here, that means they're absorbing orange. The frequency, the wavelength is 600. Deep blue, you will have orange, that means a lower frequency, lower means what? Higher energy. That means that this one here will split the energy with bigger, and this one here split the energy lower. Okay? So you can see the difference in wavelength here. Okay, so this is ammonia. The split, this is just water. So different ligands will split in the E in different. They will also ask you why. Okay. So now I told you about color already. Now how are the questions asked? Okay. I finished all the tier of color. So I've got about how many minutes more? About 20 minutes more. So let's do a few questions now. This is quite a common answer. Ask you why. Okay. Why TM are colored? TM ions colored. Now let's go to the first question. Okay. First question is here. Okay, 82. We do 82 first, okay? Before we do 81. Here. Okay, explain the detail why transition elements are colored for 3 marks. Now, this is the first answer here. Okay, 3 marks, they give you 5 points. Memorize them. Firstly, why? The d orbitals, right? The d orbitals are split into 2 different levels. If I were you, they will split because why? Because the ligands, right? The ligands, the lone pair approach the octahedral complex and cause repulsion, right? The ligands, the lone electron pair of ligands or ligands, whatever, approach, right? The octahedral axis, where what? Where dz square and dx square minus y square are. Therefore, repulsion, higher energy level. Okay, the orbitals split into 2 different levels. That's all they want. Because the d orbitals can split into 2 levels because of the ligands cause repulsion. Okay, short form lah, as long as you talk about some degree mark already. It's of course light, what light? The part of the visible light, part of the visible light is absorbed, right? And cause what? Electron, 1 mark here, electron to be promoted from lower to higher level, 3 marks. Then the color observed, see, color observed is the complement of the color absorbed. See now? And the difference in energy between the two levels is down here, okay, or HC over lambda. This is also 1 mark. There are 5 points here. You give any 3 points, you get full marks. Fantastic, isn't it? Okay, right? Now, we come back to this one later, okay? Now, next question. So, memorize that. I got one student like this. Sir, I just memorized 4 points. The orbitals are split into 2 parts because of the ligands approaching the octal complex. 2, right? The part of the color, part of the visible region light is absorbed, right? Because electrons are promoted from a lower energy to higher energy level. 3, okay? The difference in energy level is equal to E equals to H over C over lambda, and lambda is the wavelength of the absorbed frequency or wavelength. 4, the unabsorbed light, which is the seen light, is complementary to the absorbed frequency. 4 points. Okay? Okay, up to you now. Right? Okay, next one we do is page 100. Okay, the marking schema. All right, page 100 is 101 here. All right, now here, of course, they ask you all the orbitals. On the following diagram, draw clear labels and show the shape of symmetry of atypical. You know what to do? Okay, you can put here X. Okay, it's up to you one. Label X and Y here. Okay, you can put like that here. Yeah, 2 marks, diagram 1 mark. Okay, label, sketch, and okay, label the shape. And say this your DXY. Okay, or you can write any one here, okay, here now. Okay, your DZ. Label here Z is your X. Okay, or you can put, you know, here, which is your dx squared minus y squared. See now, okay? So just atypical. Okay, right? Not moving. Come on. Okay. Okay, don't know why it's wrong with this. Okay. Then it says here, although the 5 orbitals are same energy in isolated, okay? Right? That means there are no ligands there, isolated, where the transmission element is an octal, right? Complex that means got ligands split into 2 groups then draw orbital, split up, can? Easy there. Now, why is it colored? And then not in this, now here is 7 marks, okay? Right? So it's 3, it's normally 3 here, 3 here, 3 here, and 1 here, okay? Right? Now, why transmitters are colored? Let's look at this. Okay, see now. Now here, for example, also allow DZ squared. Anything we do. See, okay. Shape loops. Okay, correct label. So the shape is 1 mark. Yeah. Okay. Shape is 1 mark. Right. 4 loops. What's the 4 loops? Of course, DZ squared is no 4 loops. And then correct label 1 mark. So this is 1 mark. This is 1 mark. Okay. Now then the split into 2 levels. Okay. Marks for 5 degenerate object. Okay. 3, 2, 3, 2. Okay, marks for the 5, there are 5. Okay. Now, white color. All right, same thing. Okay. Color emitted to absorb. Color due to the absorb. Okay. It means what is absorbed, what is observed is not, is what is observed, what is observed is not absorbed. Okay. Okay. Okay, then why? Well, this is blah blah blah. This is the energy, okay, so forth. Okay, so electron promoted from lower the higher energy level. Okay, so the formula is what? E delta E is equals to H, of course, C over lambda better this frequency one. Okay, it doesn't matter. Okay, so this is, of course, then this is the frequency. This is the wavelength, not frequency. If it's H, F is frequency. Okay, right? This is absorbed. Okay, electron promoted. Okay, now why is it different color for different? See here, they ask you why. Okay, white color, 3 marks in. the color of complex given TM often changes with ligands around it. Why? Simple reason here, right? Okay. The color depends on the size of the delta E, and the delta E depends on the ligand, right? Some ligands I told you NH3 will repel it more, okay, will cause a bigger lid, okay? Therefore, it will also change the frequency or the wavelength in this one here, okay? So the ligand affects the delta E also affects the frequency by itself here. So these two are into 1 mark each, okay? Right, 7 marks. We got 7 marks, 1, 2, that's why they all come down of 7 marks, 2 here, sorry, okay, 7 marks, okay? Okay, next question. All right, page 100, 113. Okay, I'm going to show you all types of questions. Octahedral, why is it green? The specificity, nickel, hexa, aqua is green. Explain the origin of this color for 3 marks. So it must be green. You must say why green. Okay, now why green? See here. Remember, of course, green, you absorb a color, no? So electrons are transferred, move from lower to higher. Now, that means what is absorbed and what is not absorbed. Okay, right? So absorb, right? They want electron to move, the electron move from lower to upper level, absorb the complementary color of green, see now. Absorb, of course, green is a red or blue, either one of them. But then complementary color of green is seen. That means absorb the light, and then the seen color is the green. Okay, green color is the complementary of the absorbed, okay, or the green light transmitted. So 1 mark. What is absorbed? What is unabsorbed? What is unabsorbed? What is absorbed? What is unabsorbed? Which is the seen or the observed. Okay, which is the complementary color. I thought Li, no, complementary color. Okay, so it is very specific. Okay, if you say why blue? It absorbs red, and you see the complementary color, which is blue. See, color is very important. All right, next one. 100 is 113. This, sorry, 100 finish already. Okay, 114. Okay, here we are. This is quite simple. Okay, what I mean by degenerate, right? Then here, degenerate. Degenerate. Here. Okay, degenerate. Orbitals having same energy level, that's all. Okay, same energy level. All right, orbitals, they actually say quantum states, the orbitals having same energy. Okay, degenerate. Okay, right, this here part here. All right, now here, this part here. Okay, so forth, now here. They ask you why. When the solution contains complex copper 2 minus, of course, this is copper 1, isn't it? Right? Because CuCl2 minus, this is 1 minus, okay, it's plus. Copper plus is 3D10, Okay, because you lose the 4s1. Okay, so here precipitate of Cu shown and it's white. Okay, why? Because why? Copper 1 plus is the 3D is what? 2 marks, no? Okay, it's completely filled in. Therefore, must say no electron transfer or no electron promoted. You must say this. See now? So they give the answer here. This is what here? I think on the same page. 14, here. See what? Okay. Okay, here. So 3D shell. For your copper, Cl2 minus 3D. Full. 1 mark for this. Electron cannot move, no? Right? No electron transfer, no electron can move, no? Because it's all packed already. You can only go to 4s1. And to go 4s1, what is the frequency absorb? It is the UV. It's why colorless. Okay? Right? Right. Now here. Now here, now they give you the absorption spectrum. Now there are two questions with this absorption spectra. Okay, now here's one of them. The complex chromium aqua, this chromium 3+, is colored because it absorbs visible region. True or not? Absorption spectra is shown below. That means this is see violet, they give you violet here, and this right here. Oh, this is unabsorbed. No, this is unabsorbed. Unabsorbed. That means what? Unabsorbed, S-O-R-B. That means it's what is observed, isn't it? Right? Of course, find out here what is green, isn't it? Green or yellow, up to you. It means what you see is a green color, green or yellow. So they ask you, suggest the color of its complex. Easy, 2 marks. You must say what is absorbed and what is absorbed and what is unabsorbed. Okay? See. Not so. Okay, see now. Right? For 2 marks. You see green or yellow. Up to you because we have to tell now. And say red or orange and blue, both of them are absorbed. See now, absorbed. Both of them. You must have the end there. Why? Because you can see here, right now, this blue, isn't it? Blue and what? Red or what? Are absorbed. So you must say what is absorbed and what is observed. Observe is green color. You must also say absorb. The two here. So the two hills here, you must say it because the mark is given there. See? Oh, sorry. See? What's observed and what is absorbed? And see now, 2 here. So the mark scheme is very clear. So you must know what they want in exams. Okay? Well, let's go for 2 or 1 more. Okay, this one here. Right now, up here. Let me see. Let's go 128 first. 128. Okay, again here. Of course, this one here, remember, is Ma4B2. Of course, the cis trans isomer. Okay, right? Remember, Cl here, and then of course, Cl here and Cl here. Okay, this. Okay. So why are they different? Explain why these complexes are colored. Same old question. Why different colors? Okay, similar here. Because they split. The position can split differently. Okay, position wise. Okay, see here. Right? Why color? Again, same old thing. So I say you better memorize it. Okay. In complex, the operators are split into 2 energy levels. Why not? Color absorb in the visible region. Okay. What happened? Electron promoted from lower energy level. Okay, right? So why the different colors? Right? Because the DD energy block is different for 2 complexes. Because why? Different position. Now is see, one is cis, one is trans. Okay, one is that. One is that. No. So different position will split it. So the energy gap is different. It's split into different for 2 complexes. Hence different colors. Okay. Position-wise also will split it into different colors. All right, so first one here. The last one, of course, 158. I think so. 158. This is about, okay, 158. Oops. Complex, 158. Same all, okay. Here. All right. Explain why many color, same marks in it. Right, using ideas that suggest why color complex is okay. Right now, see, they say it's blue. This is very specific. Explain why the cobalt. Remember, cobalt chloride is CO-4. Okay. Now remember, tetrahedral and octahedral split differently. I should have to. Okay, I forgot to tell you about this. Why is it blue? For 1 mark. So blue is the unabsorbed part. Is the transmitted part. It means blue is the unabsorbed. So you see blue in. So the answer is that. See? Why blue? See? Blue light is not absorbed. 1 mark. That's how you answer it. Okay? Don't say, oh, because I see blue, you idiot. Blue light is not absorbed. Okay? So it absorbs the complementary. It will absorb the complementary color of what? Or blue. You can put this up, which is actually red or green or anyone do, okay? Okay? Right? Okay? Now, let me just go to one more, which is page 81, which is the other one, which is talk about spectra one, okay, 81 here. Okay. Okay, the two actually 81 here and down here. Okay, two of them. Now this one first. Right? Now it says here, the graph shows the absorption spectra for two complexes containing copper. This one is famous. Okay, your copper tetraamine, which means they absorb yellow-green part, the blue part, and the red part not observed. That means that they become very deep blue. Right? This is deep blue, isn't it? Deep blue. And they're very strong. They ask you why so strong. Now this is your aqueous. See, it absorbs, the main part is in the infrared, no. It means only a bit of this red is absorbed, and the blue part, all this here is not absorbed. It means you see all this thing. So it's pale blue. Right? Now they ask you the question here. Set the colors, of course, this is pale blue. Pale blue. This is your deep blue. Okay? You see the spectrum above, give two reasons why the color is deeper, more intense than this one here. Now look at the marking scheme, okay? This is what here? 09. Okay, here. Okay, so pale blue, see not? Pale blue is very important. It's pale blue. One mark, deep blue. Now see, because it's a larger absorption peak, right? Larger absorption peak. Why I mean so? See here. I'm going to rub it off first. See, we got the same amount of solution. Yeah. Okay. Here. Okay. Same amount. Here, same amount. So this one here, this one here. And got the same amount of light comes here. Very strong one. Okay, let's say it contains 1,000 units. Here's a 1,000 units. Okay, very strong light. 100 units, right? Right here, out of 100, right? This height now here is here is 100. Okay, here is 80. Right, here is only 20. That means this fellow here can absorb 80 of this one here. That means absorb 80 of this yellow-green light. That means the blue and the red coming here is also 80 now. That means very strong, isn't it? Right? 80 units now, quite bright. But here, out of 100 units, absorb only 20. Right? Absorb the red here, a bit here, absorb 20 only. So how much is transmitted? Or also, see, the other 10 is here, or 20 here. The other 80 is here, but here only 20. So what comes here only 20%? Right now. See? So this absorption peak here, very much. That means a lot of light is absorbed. So here, only small amount of light is absorbed. Secondly, of course, this fellow here absorb the maximum here is in the visible region. This one here is in the absorb is not is in infrared. So that's why it's very weak. Okay? I see the marking scheme. See? Because one large absorption peak. Okay? Right now. Large absorption peak. One like complete like that. Secondly, the frequency maximum is in the visible region. The other one is about I think 600 or whatever. This in the infrared. Okay? Right? All right. Next one. I ask you here. Predict absorption spectra for Cu NH32. Now I told you actually it comes from this one, isn't it? Right? One by one, the water ligand will be kicked out by the ammonia. It doesn't come at one shot, so it can go from 1, 2, 3, and 4, maximum 4. Don't go 6 again, right? So I ask you to sketch the spectra for this one here. Of course, it's between here and here, right? So you must see here. So here the maximum is about 800. Here is 600. So about 700 lah. Here, okay, the maximum. And the height here is 80. Here 20 means around here lah. Let me see. Go from here. Okay, here to okay in between. Go from here. I'll put another color. Why no blue? Why no blue? Interesting. Blue. Okay. Okay. So halfway between here and here, and halfway between here and here. Look at marking schema. Right? A curve, the maximum, right? from 600 to 800, okay? And, you know, so this is a wavelength about 700, okay? And of course, the height between the two, okay? So that covers everything. Of course, down here you can look at it yourself. It's quite simple, okay? Here. Okay, the table shows the photons and blah, blah, blah. Remember, high, isn't it? High energy, isn't it? Why? Because it's near the UV, okay? Going down low here. The visible spectrum of the two transition metals C and D are shown in the diagram. C here and D here. Of course, here, of course, is your what? Is your purple, isn't it? Here, okay. Violet. And 650 is what? Doesn't move, why? 650 is what? 650, sorry, 650 is a red. Okay, here's a red. Okay, these are possible colors of these complexes as follows. Choose one of these colors to describe the observed color for student C. Okay, if it's observed, this absorb here, which is what? Which is your yellow green, right? And what's it with red? Unabsorbed, isn't it? So this red. Solution is red. And D is absorbed here, and what you see is your blue. See now? Or indigo. Or indigo. 400, isn't it? 400 here. What's that? Is your 450, 400 here. Is your violet. Okay? In which complex will the energy gap be larger? Okay? Now remember, if you absorb the lower wavelength, higher than it means C, it's not absorb here now, right? Lower wavelength. Right? So means here break here is C, so here is bigger. E here, HC lambda. D will be C, D will be lower. D, okay. Why? Because the wavelength here, E equals to HC lambda. Here is higher wavelength, okay? 650. Here's 450. So a lower wavelength means high energy. So here split more. C will split more. Okay? Okay? Right? C split more. 07 May June 4. Okay, let's go 07. I don't have it here. 07 May June 4. 07 May June. Yeah? 07 May June 4. Okay? 07. Where is you? Where are you? Okay, 07 May June 4. All right. A few more minutes, okay? All right. See. Okay, see? Red, blue, they want blue. Okay? Right? C, right? Absorption is a lower wavelength. C, isn't it? C? Right, C, isn't it? This one, they want blue. Actually, violet should do lah. They want blue. Okay? 450. 450 right here. She's holding. Never mind. Deep blue. Okay? Right? C, isn't it? Right? C, bigger split, smaller wavelength. Okay? Right? Smaller wavelength. Where's the fella? Okay, right. I see. Wrong one, is it? Here. Okay, lower wavelength. Okay, so we have finished on color already. The next one we'll go will be on catalysts. Okay, so goodbye. I hope you keep on studying. Okay, I'll stop screen share first. Stop.